Okay, let's take a look at this problem. It gives us a voltage equation with respect to time. So I'll write that out up here just so it's a little bit easier to see. So V of L is equal to 10 cosine 2000 pi t. There's an angle of 0, so I'll just put plus 0 there, and that's volts. Okay. The inductor is 100 millihenries. All right. It wants us to find the complex impedance of the inductance. Complex impedance of the inductance. Find the phasor voltage and current. We're not going to construct a phasor diagram. They want us to write the current as a function of time. Okay. And we're not doing that. And we're not going to do that. So, and then at the very end, we're going to state the relationship between the two. Okay. So just getting rid of all the stuff that we're not doing. All right. So here, the first part, they want us to find the phasor inductance. So Z of L is equal to J omega L, just from that formula sheet. So J omega will come from up here. So it'll be 2000 pi radians a second. It's everything that's before the T. So 2000 pi. So 2000 pi. And then L, which was 100 millihenries, which is just 0.1 henries. That will give us J 200 pi ohms. All right. And that is our complex impedance value there. That is part one. Okay. Now it says we attach those two together. So I'm just going to assume that it's like this. Because this is the only way we can't attach them, really. This is our L, this is our V. Okay, so all the current is going to go to that inductor, but that means that all the voltage is also going to be absorbed by the inductor as well. So V of L is just equal to V source. So therefore, V of L is just equal to 10 at angle 0. That 10 at angle 0 comes from up here at the top. This is the phasor form here. Because up here, it was 10 volts at angle 0. So that would just be the phasor form. And like we said, all the voltage from the battery is going to go straight into the inductor. So that's why we know that. And then it wants us to find the phasor current. Okay. Let's find this current, I here. I of L is going to be equal to V of L over Z of L. So 10 at angle 0. And remember how we said that J is going to be equal to 90 degrees. So 200 pi at angle 90 degrees. It's going to be 10 over 200 pi. We'll subtract those angles. I'll get 15.915 at an angle of negative 90, and this will be in milliamps. So this is I of L in the phasor form. So those are our three phasors. Or two phasors, but all of our values they asked for. All right, and they want us to write current in a time function. So if we write I of L in terms of t, it will be 15.915 cosine 2000 pi t. Notice we're just pulling the 2000 pi. It's going to be the same frequency. And then minus 90 degrees. Okay, because we're just pulling that 90 degrees from here into there. And this is milliamps. All right. There we go. And let's state the phase relationship. So let's look at our two phasors. So we'll compare these two values. And we'll notice that the voltage, so if I went and shapes, this one, yeah. So if I went and drew this out, let's just use our imagination here. So V of L, that's V of L at angle 0. And then our I of L, granted these aren't to scale, but it's I of L here at negative 90 degrees. So this is 90 degrees right here, the difference between those two. So we see that our voltage is ahead of our current by 90 degrees. So voltage leads current by 90 degrees, or you can say current lags voltage by 90 degrees as well. Okay. And if we actually check that out with Eli the Iceman, so ELI, this is voltage, this is current, and this is your inductor here. Your voltage is ahead of your current, which is what we set up here, and then your current is behind your voltage. So we are good there as well. All right. So those are just all of our statements being made, and that's a pretty common question that they'll ask you.